All right, so thanks for the invitation and thanks for the introduction. So first, I'm going to start with 2 minutes of something between philosophy, motivation, and warm-up, which is one thing we saw even in Ilya's talk, which is a very, very old result that let's say I have some function h I have some curve, I don't know, gamma, and have some function h from gamma to gamma. And I want to know, what is the harmonic extension of h? That you can actually see this with Brownian motion. So if I have Brownian motion in D, and I just run it until it hits gamma. So I just say that t is the first time that it hits the boundary of D. Then I can build this function, which is some harmonic extension, by saying for any point z in this domain, I just run Brownian motion. It does what it wants to do. At this time tau, it's going to hit the boundary. And my harmonic extension of my function is just the expected value starting from z. So I want to know its value at z. I look at the expected value starting from z of the value of my function evaluated at Brownian motion at this stopping time. So yeah, I don't mean that. I mean the real numbers. Yeah, sorry about that. Thank you. Yeah, this is just a real valued function. I'm not doing anything complicated. This is a result of Kakutani from like the 1940s, and I'm just trying to say this as some motivation that you can sort of use Brownian motion to see things in potential theory or about harmonic functions. So another way you can think about this, if we did this just in the disk, then we can write this in a very explicit way. So what is this h of z? What you do is you integrate your function h against a very explicit function. And this function is the Poisson kernel. And so the Poisson kernel is basically measuring, what is the sort of mass, sort of how many Brownian paths are there from some point z to this point e to the I theta on the circle. And the same thing is happening here. Brownian motion is conformally invariant. And so what's happening is that I have some conformal map from the disk to my other domain. And I still have this result. This expected value of Brownian motion is the same. It doesn't, that doesn't change. But if I think about it in terms of this kernel, that transforms in a very simple way. So if my original function is this, and this is telling me about about Brownian paths from z to the circle, z to this point e to the I theta in the disk, then if I wanted to know it in my new domain D, and I have this conformal map between them, then my new Poisson kernel is related to this one by, it picks up sort of a factor of the derivative at this point e to the I theta. But otherwise, it's sort of the same thing. So it transforms in sort of an understandable way, well, as long as we could understand these conformal maps, which I guess we saw in Ilya's talk can be difficult. But I'm just trying to say that somehow, sometimes there are these things in analysis or harmonic analysis where you can kind of understand them and measure them using Brownian motion. And that will be kind of something that I'm going to use. I'll tell you what this Brownian bubble T is, and I'll explain how you can kind of use it to tell other stories like this. That's what so. This is my very, very general warm-up. Let me tell you about another example of this sort of phenomenon. Instead of looking at Brownian paths, I'm going to look at Brownian loops. So this is going to be a measure. I'm going to be looking at at loops L in the complex plane that look locally like Brownian motion. And there's a measure on these called the Brownian loop measure that has a bunch of natural symmetries. So I'll tell you a little bit about the Brownian loop measure in a second. Let me tell you about this, I guess, sort of, I don't know, result in this vein, in something sort of similar to this kind of idea where you're sort of using Brownian motion to measure some quantity in terms of this Brownian loop measure. Then I'll tell you a bit more about the Brownian loop measure and how it's going to be related to this Brownian bubble T. So what is this? We saw this, I think, in maybe Franco's talk, and we saw something similar to this in Paul's talk as well. But this is the Loewner energy of a curve, gamma, like the one I drew over there. It's a Jordan curve. It's something that's related to sort of to Teichmüller theory in geometry, and it also comes out of SLE. But it's a deterministic quantity of a deterministic curve. But it's sort of measured in terms. You can also sort of think of it as being measured in terms of Brownian motion. So when I write quotes, I'm going to write something that doesn't make perfect mathematical sense. But what you can look at is the sort of mass of Brownian loops that hit the circle. So okay, times mass of Brownian loops that hit the circle minus the mass of Brownian loops that hit gamma. And somehow what this Loewner energy, which is somehow measuring sort of how close your curve is to the circle, a very heuristic way to think about it is that it's measuring, how many Brownian loops are hitting your curve versus hitting the circle. This quantity doesn't actually make sense. When we have this Brownian loop measure over here, this is an infinite measure. It's not a probability measure. And sort of the reason it's an infinite measure is that there are lots of really, really short loops, and there are lots of really, really long loops. So what I'm sort of subtracting here, in this picture, if I only have a single curve and I'm looking at any loop that hits this curve, that could include really, really tiny loops. That could include really, really long loops, et cetera. And so to make sort of rigorous sense of this, we have to sort of regularize it a little bit. And a theorem by Yilin is that it's possible to regularize this. I'm not going to use that regularization, so maybe I won't talk about it right now. But the idea is somehow that instead of looking at loops that just hit the circle, we can get rid of the small loops by asking it to hit the circle and another slightly smaller circle. That gets rid of the small loops, and we do the same thing over here. We ask it to hit the curve and another curve that's slightly smaller than it. And then to get rid of the big loops, if we say that all the loops have to avoid some tiny disk, that's actually enough to get rid of the big loops. And so somehow, if you make these two modifications, that you sort of ban the small loops by asking for it to hit two very close to your curve and some perturbation of your curve, and then you get rid of the large loops by saying it's contained in some domain that is almost everything, but a tiny bit less, then this can become a rigorous mathematical statement. But okay, so what I want to tell you about is I will tell you what this Brownian loop measure is. And I'll tell you about what the Brownian bubble measure is and how it's related to the loop measure. And then I'll show you how you can use this relationship between these things and the Brownian bubble T, at least in a heuristic way that you can also regularize, but which I want to explain to sort of interpret some other statements about quantities like this in terms of the Brownian loop measure. OK, so that's my very vague intro. So let me be a little less vague now. So let me tell you a bit more about Brownian loop measure. So I told you it's infinite. How do we, what are the kinds of things what are the kinds of quantities that we can make sense of? Well, if you restrict it to some domain, like let's say I have some domain D, and you look at Brownian loop measure, but restrict it to D, by that I mean you only look at loops that are contained inside D. That gets rid of the long loops. I'm going to call this measure mu loop sub D. So this is the loop measure restricted to D. This is still an infinite measure because we still have the small loops. But if I have some situation like I take two sets A and B, and I look only at loops L, which hit both A and B, this will be something finite. So an example of a set with finite loop measure is I look at the loops that are contained in D, and they hit two disjoint sets A and B. This will be finite. So this is just to give you some intuition for what kinds of things are actually finite. But what is special about this loop measure? What's special about this loop measure, it's actually characterized by two very simple symmetries. So the first of these symmetries, which I sort of alluded to here, we can restrict it to different sets, and it behaves in a really nice way. So if I have some domain D prime contained in D, then the loop measure on D prime is the same in distribution as the loop measure on D restricted to loops contained in D prime. So we can restrict, so it makes sense. I can talk about this loop measure on the whole plane. I can talk about a loop measure in domains. I can restrict to other domains, and all of these things make sense. I'm not making any decisions or choices when I do that. And the other, maybe more surprising and symmetry is that it's conformally invariant. So I'm putting under the rug a little bit. You know, when you think about loops like this, they locally look like Brownian motion, so there's some time length of this path. That's not the same thing as the spatial length. When I talk about loops being really small, I'm talking about their spatial length as well. But here we also have some time length. So up to changing the time parameterization, if I have a conformal map, then up to reparameterization, the loop measure in psi of D is just psi of the psi of the loop measure. Sorry, this is getting a little messy. So by this I mean that if you take a Brownian loop here and you just push it forward by the conformal map up to changing the time parameterization in a well-defined way, the same way you would do looking at the conformal invariance of Brownian motion, that new loop is distributed like it was taken from here. And one more thing I think I forgot to say in defining this measure is that it's a measure on Brownian loops, and they're unrooted. There's no special base point. Okay, so it is the only measure on unrooted Brownian loops that satisfies these two symmetries. That characterizes what it is. And now let me tell you about what the bubble measure is and how these things are related. I should also say, so the Brownian loop measure, I think, was introduced by Greg Lawler and Yilin Wang in some context related to studying SLE. And I'll say a little bit more about this later, but for now, I don't want to get sidetracked on. I'll comment on this a little more later. And the bubble measure, which I'm going to tell you about now, also appeared in their work. So what is the bubble measure? For the bubble over here, I was talking about any domain D. To define the bubble measure, I want to start just in the disk. So I'm in the disk. I pick 1 to be a special point. This is a point on the boundary of the disk. And this is going to be a measure on Brownian loops rooted at 1 in the disk. So what do they look like? They look like this. They're contained in the disk, and except for the point except for the point 1. So I'm going to write this as like this. And this is, again, an infinite measure. It's not a probability measure, again, because I have no restriction on how small this loop can get. So if you want to define this, a little bit more carefully, it really comes with some kind of regularization. So one way you can do this regularization is I imagine I look at this annulus, and this is with, say, 1 minus r here, and this is my annulus a sub r, and I can kind of define this as a limit as r goes to 1 of these guys that actually exit this annulus. So this red one would be in this support here, but this yellow one would not. It's too small. So this we can define in a more rigorous way, and then we're sort of taking a limit as r goes to 1. So one way you can think about, okay, what still is this thing? I guess in my warm-up / motivation / whatever you want to call it, we talked a little bit about these Brownian paths that go from some interior point in the disk to a boundary point. You can sort of think of, if you want to think of what is the Brownian bubble measure, I had some measure here that has finite mass. It's given by this Poisson kernel on Brownian paths from z to this boundary point here. So what I'm doing to define the bubble measure is I'm taking a limit as z goes to the boundary, and then as z coincides with the boundary point. So when you take a limit like this, what you can't actually ask your Brownian motion to start on the circle. You can't restrict to that. You have to condition on that. So when I move z inward, it's sort of like I'm taking a derivative of this measure. We sort of already took a derivative here to move this first point to the boundary. So what I want to say about this is, so this is an infinite measure. Like the Brownian loop measure, it has a restriction property. And then the next natural thing to ask is, how does it behave under conformal maps? So I'm putting a little bit under the rug here about this regularization, but I think it's not worth worrying about for the purposes of this talk. But if I have a conformal map, let's say I want to define the bubble measure somewhere else, not just in the disk at 1. If I have a conformal map psi from the disk to some other domain D, then I can think of the bubble measure. What is the bubble measure? How does it transform? Well, it's going to sort of pick up a derivative factor twice, because both its endpoints are on the boundary. So if I want to look at this bubble measure, it will pick up a factor of, okay, maybe I shouldn't use z because I've used that. I'll just call this 1. This, with this sort of extra multiplicative factor, is what you would get if you just sort of pushed all your bubbles forward from here. It's a psi. Thank you. So what the picture would be is I have some other domain D. I have some point. I have my map C here. I have this point C of 1. And if I want to look at a bubble here, it's just that I take this bubble here and I push it forward by the map. But the sort of the way this measure transforms, it transforms with this factor. Yeah.
The restriction property you have to require to stay with some boundary point in common?
Yes. Yeah. So if you want to restrict, the domain that you're restricting to still has to contain the boundary point where the bubble is rooted. Yeah. So in the loop measure case, I can restrict to whatever domain I want because there will always be loops, but there will not be bubbles unless you contain the base point where the bubbles are based. Other questions about the initial setup? Okay, so now let me tell you about how the bubble measure is related to the loop measure, what's already known, and then I can start to tell you what the Brownian bubble T will actually be. So as sort of a small modification of what I think that I just attribute this to Lawler and Werner, but it's in a basically almost like a change of coordinates of what they've written. Let's say that I take, if I define, okay, I have you have the circle. You can look at maps that shrink the circle a little bit. And I can just foliate inside where I have each of these circles. This is the unit circle S1, and this circle is like e to the minus t S1. And I just keep going for t from 0 to infinity. And I define these maps, ft0 of z. This will just be e to the minus t S1, or e to the minus t times z. So it's just a scaling map. And what they've shown already is that if I look at the loop measure on the disk, and this is the same thing as an expression I'll explain a little bit more, but I integrate from 0 to infinity, from 0 to 2 pi, 1 over 2 pi, times I push forward the bubble measure by my scaling maps, and then I just integrate d theta dt. So let me unpack this a little bit. So these are equal in distribution, both viewed as measures on unrooted loops. So this is already a measure on unrooted loops. A priori, this is sort of a measure on rooted loops, but we're going to forget the roots. So let me draw a picture of this. So what you can imagine is maybe I have a Brownian loop here, which I'm going to call L. And if I look at this Brownian loop L, it's sort of a property of Brownian motion that, except for excluding some measure 0 collection of these loops, this point is going to have some unique point of maximum modulus. So there's going to be some t where I can kind of naturally view this loop as rooted. So this gives me my t, and then I look at this map ft0 from this, let me draw another color, from here to here. Okay, and I have some yellow point here, which is EDI theta. This point is like ft0 of EDI theta. And then the orange guy is distributed as if he was sort of pushed forward by this guy. This guy is like ft0 inverse of the loop L. So the idea of this measure over here, what do we do? On this side, we just take some loop in the disk. And it turns out that it's sort of a property of Brownian motion that I can find this yellow point on that loop and pull it back and get something that's in the support of the bubbles. On the other side, sorry, this should be a star. On the other side, the idea is that first I go sample a bubble at 1. And I sample a bubble. And then I rotate it to e to the I theta, and then I push it forward by t. And how am I deciding how to pick a bubble, and how to pick a theta, and how to pick a t? Well, what this measure is sort of shorthand for saying is that I have this space, 0 to infinity, of times t. And I just have a Lebesgue measure on this, dt. And then I have the circle. I have to pick an angle. And I have a measure on this, which is just uniform measure, 1 over 2 pi. And then I have some abstract space k, which is the space of, maybe this is the space of possible Brownian bubbles at 1. And I sample something from this, from the bubble measure. So I have this sort of, if I want to sample from the loop measure, I could sample directly from the loop measure. Or I could pick a time, pick an angle, and pick a bubble, and push it. And the result is that these are the same. OK. So I can start to tell you now what the Brownian bubble T is. This is one instance. This is sort of like one example of a Brownian bubble T. So this is this. Another way you can think about this result is instead of thinking about just this loop measure, you can think about this in terms of Poisson point processes. So there's a Poisson point process on Brownian loops called the Brownian loop soup. And it's you're on the space of Brownian loops, and you can look at any subset of that space, and how many loops are you supposed to see in that set? It's some Poisson random variable whose expectation is mu d loop of that set. So this is a Poisson point process with intensity given by this mu d loop measure, and this thing here. This thing will be, this is a Brownian bubble T. Maybe not the most interesting one. I'll try to explain in a minute what so this is a Brownian bubble T. And it's a Brownian bubble T, and the other data that goes into defining the Brownian bubble T is that we picked this choice of foliating by concentric circles. So this is the Brownian bubble T along the concentric circle foliation. And this is a Poisson point process with intensity given by the other side of that equation that I wrote before. So let me just give this a name. OK, and so these two things, as Poisson point processes, are the same. So the real question of Brownian bubble T is we don't want to just look at the foliation by concentric circles. We want to make this more interesting. So what happens if we fill the disk in a different way? So I'm going to write this as BBT means Brownian bubble T. So the picture to have in mind is, I start with the disk, the circle, but instead of having my family of curves just move inward as concentric circles, they can be more interesting looking. And so I need to tell you how do I explain what is a foliation? What do we know about what do we know about the foliation as some properties of how I describe it? But basically the question is if in some ways this Brownian bubble T is sort of like an iterative process. It's saying that if I go inward and explore the disk looking for loops and catch them at their sort of maximum point, or I produce them at some rate as I go inward, that's the same thing as if I just sort of did an exploration and went inward. And the question is, at what if I'm going to explore in some funny way, if I wanted to just create the loops along my funny exploration and get the same thing, at what rate should I create loops? Is it possible along some funny foliation to still sort of spit out bubbles at the right rates, at the right points, so that I actually get the loop measure back? So to explain this a little more carefully, I need to tell you, what do I mean by a foliation, and how are we going to build these things? OK, so this is maybe one of the parts of the talk where I have to build a little bit more machinery. So please let me know if you have some questions. But how are we going to build these foliations? It's going to be by something called the Loewner-Kufarev flow. So how does this work? Well, actually, let me just start by drawing some pictures, and then I'll explain to you sort of how to formalize it. But sort of the first idea is, okay, I have this sequence of curves. Maybe my outer one doesn't have to be the disk. It doesn't really matter. So let me just draw something kind of general looking. I have this sequence of curves, and I want to sort of describe the evolution of this family as I move inward. So I'm going to do this with conformal maps. So let's say I'm going to start with the disk. And for each of these leaves, I have for each of these domains that are shrinking, I'm going to have a conformal map that goes from one to the other. So maybe this is let's say this is D0, this is dt, this is ds, or something like that. So I'd have a conformal map F0. I'd have a conformal map Ft. I have a conformal map Fs. So these are all conformal maps. Their domain is always the disk. And what I want to know is how can I encode in terms of these conformal maps sort of how to take the domain D0 and sort of shrink it toward dt. So we have this family of conformal maps, dt, from D to some domain dt. We have these, for now, let's just say for all t and r. And we're going to say that they satisfy an equation. And I'm going to explain what this equation actually means, because I think otherwise it looks a bit mysterious. They satisfy a PDE in t. What is this? It's d by dt of ft of z is equal to minus z ft prime of z times some function ht of z. So this, I'm going to explain what this function is and how to think about this in a moment. But for now, this is an analytic function on D such that its real part is positive. Okay, and this is supposed to hold for z in the disk. Okay, let me explain what this actually means geometrically, because I think that is helpful. So what's the idea? So let me simplify this picture a little bit, actually. I just want to have one curve. Okay, and here's my map. So what does it mean? Well, so if you're in the disk, what is this sort of inward direction? If I'm at some point in the disk, which way points inward? Well, I'm just going to point in the direction minus z if I'm at z. So let me just assume for now, even though it's a little bit sketchy, that z is on the boundary, just so to make it a little bit simpler. So if I'm at z, the inward pointing normal direction is minus z. Okay, I apply my conformal map ft, and I find the point, some point ft of z. What is the new inward pointing normal direction? Well, it's ft prime of z. It's minus ft prime of z. So it could be rotated a little bit, but this is the normal vector. And so what is this equation saying? It's saying, okay, move inward. I want my sequence of domains to be shrinking. Move inward, and how much should you move inward? Well, you should move inward according to this function. So this is some analytic function, so it's allowed to rotate a little bit. I'm rotating a little bit. This is my new vector, minus z, ft prime of z, ht of z. It's allowed to rotate a little bit, but the fact that it has a positive real part is telling you that its component in the inward direction is positive. And that's what's telling you that the sequence of domains is going to shrink. Okay, so this is some family of conformal maps. They're going to satisfy a PDE. How am I going to sort of talk about them and catalog them and describe them? Well, I can describe, ft solves this equation for a specified set of HTs. So there's a really nice way to package what we mean by a set of HTs. And this even comes back to the thing I said at the very beginning, but I guess I've already erased. But what is HT? It's an analytic function with positive real part on the disk. And what that means, up to some normalization, is that this HT of z has a very explicit formula. I'm just going to look, which is that I can write it like this. and multiplied by integrated against some measure rho t of theta. And this rho t of theta, this is a probability measure on the circle. OK, so let me just explain one more thing about how to think about this. This, I don't remember if I wrote this. I think I wrote this formula earlier, but I don't 100% remember. But if you take the real part of this thing, then this is actually basically the Poisson kernel I wrote earlier. So this is actually, so what's happening is if I take the real part of this, and remember the real part is telling us like how much inward we're going. If I take the real part of this, I'm getting the harmonic extension of rho. So rho is really what's telling me like how fast I'm moving inward in this normal direction. And I have a little bit more flexibility because ht tells me I'm also allowed to do a little bit of rotating. OK, so how we're going to think about, I think, let's see about this flow, is that actually my input will be this sequence of probability measures on the circle. And from this, my first output will be this sequence of conformal maps solving the PDE. For these measures. And my second output will be a sequence of these regions dt, which are just the image of the disk under the conformal maps. And this is how I'm going to think about how to build one of these things. So let me give you a few examples to explain how to think about the regularity here. Because right now, I haven't put any regularity here. These rho t's could be like insane singular measures on the circle. I'm going to not allow that, but let me try to explain a little bit why and what we actually care about. So the first example that we've already seen is, let's say I take rho t to be 1 over 2 pi for all t. Then what happens? Then my ft's are these scaling maps, and my dt's are disks of radius e to the minus t s1, or e to the minus t times d, sorry. And I have this sort of foliation of the disk by these concentric circles. So this is a great example. This is the most regular example we have is in the class that we won. Another example, which is maybe familiar but actually not in the class that I won, is that we could say take rho t to be a Dirac mass for all t. So if you do this, then actually what you recover, if you've seen this before, is actually the regular radial Loewner equation. But what does this sort of create? Let me just draw it. What this does is that it means that the sequence of domains dt that I get are these like slit domains. So dt will be like this whole thing here, where I have this boundary, this funny, the boundary's a little funny, it kind of goes around the slit. And as I increase t, what's happening is I'm increasing this path. And this is sort of not in the domain that I want. This is a domain that's been studied before by Lawler and Werner, and I'll say a little bit about what they understood in a moment. But this is not the domain I want for our result, because, for example, you won't be able to see all the Brownian loops if you only look at the boundaries of these dt domains. You'll only see the ones that hit this curve. So that's sort of not in the regime that we actually want to look at, because it doesn't generate some sort of foliation of, it doesn't generate sort of a sequence of Jordan curves filling the disk. This is not what we want. So this is sort of work in progress, so we're still sort of understanding what is really the correct what is exactly the right regularity condition to put on these things to put ourselves in the regime that we want for this theorem. But what looks like very likely a very reasonable choice is there's something called a foliation with, there's something called the Loewner-Kufarev energy. And maybe I'll say what it is in a minute, but it's a function of rho. So I'll say rho is this whole sequence of rho t's. And it's a theorem of Fredrik and Yilin that if S of rho is less than infinity, then if I look at, I can do this whole game, and I can look at the boundaries of these regions dt. These are going to be gamma t, will all be Weil-Petersson quasi-circles. And they will foliate the disk. So in that setting, what we have is a picture that looks kind of like this schematic picture I drew. And each of these leaves, that I've drawn here, are Weil-Petersson quasi-circles. So they're not unbelievably regular. They're not analytic or anything like that. But they're regular enough that we have they're nice Jordan curves, and they are actually filling the disk. OK, so now I can tell you what Brownian bubble T actually is. Yes. Oh, OK, thank you. I'll stop in a moment. OK, so what is Brownian bubble T? Well, it's a function of rho. I'm going to look only at rho. I'm going to look at foliations restricted to the disk. So here I'm imagining I could foliate all of C, but I'm just going to look at ones that are restricted to the disk. So that means I'm looking at T bigger than or equal to 0. And what is the Brownian bubble T? Well, it's a Poisson point process where we do where on this space, 0 to infinity, cross the circle, cross Brownian bubbles. And the intensity measure will be like dt in time. It will be rho t of theta on the circle. And then it will be sampling a bubble from here. So what it looks like is I pick a time. OK, let me do it this way. I pick a bubble. And then I pick an angle. I move the bubble to this angle. And then I pick a time. And I send it to this leaf. OK, and I've picked these. I picked the angles as a function of rho t. And the theorem of this talk. Here we had this for concentric circles, and we were using this this map ft naught, which was just scaling. Now we're going to use ft, which is the chain for our measure is rho t. And instead of seeing 1 over 2 pi d theta, which was the rho t for the concentric circles, this becomes d rho t of theta dt. And the condition here is, we believe, is this, where this plus just means I'm only looking at the leaves that are contained inside the disk. OK, so I think I'm basically out of time. But maybe the things I would, I don't know what else I want to say. Well, I guess maybe the one thing I want to say is just sort of intuition, is that sort of when this rho t is larger, that's telling you that your leaf was pushed in more at this point. And so somehow you're kind of catching more bubbles at that point. And that's why you see this rho t in this formula. And I guess the add I'll say, but not explain, is that, okay, we just showed that actually the Brownian bubble T is not a new thing. It's the same thing as the Brownian loop soup for any row. So what is this? We introduced a new thing and showed it's actually an old thing. It's actually a useful perspective on the old thing because it lets us prove new things about interpretations of sort of like some of these quantities that we can think of in terms of Brownian loops. You can compute new things with them. So I will if you want to look at sort of how this changes as you move a curve. There's sort of a known formula for this, but we can give kind of a new explanation using this Brownian bubble T perspective in terms of sort of like you looking at your curve, and somehow what's happening is that if insofar as this is sort of loops that hit your curve minus relative to loops that hit the circle, if you move your curve slightly, you sort of drop some loops. You drop loops that point out; these get dropped. And you gain loops that point in. And we sort of, the loops that get dropped and the loops that get gained, we can kind of understand as basically looking at masses of bubble measures. And how they get weighted, we can understand using this theorem as coming from the rho T. All right, so I'll stop there. Thank you.